Okay, so today I'm going to talk about implementation of distributed systems, and with Andy tells me that several of you have had trouble with doing assignment 3 and contacting him. So he wanted me to go over processes and forking and threads. So I'm going to do that. And then, and actually I was going to cover that anyway, but I'll do that right at the start. And then we'll talk about remote procedure call, transactions, and pub sub, or publish subscribe, which is another way of building implemented system, distributed systems. Okay, and so let's just get started with this. So when you have a distributed system, a typical distributed system is called ClientServer, and we've sort of seen this already with your homework assignment, because there you have the tic-tac-toe server, and you can have multiple clients. So you have some set of clients which are communicating with the server. And what we have is that we need to deal with all the clients. The server needs to deal with all the clients at the same time or in parallel. And each client is trying to do something different. Okay? So the server needs to deal with what's called parallelism. Okay? You have parallel or concurrent accesses by the clients on the server. So it needs to do something about it. Right? So in any distributed system of this sort, a client-server system, the client side is quite easy. The client is just doing, it just opens a socket typically and communicates with the server and then gets responses back. So this side is pretty easy. What I'm talking about is what happens on the server side. What the server needs to do is essentially keep track of each client state separately, right? So we can think of it having some kind of memory. And in this memory, it's saying, okay, client 1, well, if it's a tic-tac-toe game, for example, client 1 has made 2 moves, client 2 has made some other moves, and these 2 clients are playing together, and those other 2 clients are playing together, and so on. So all that stuff has got to be kept track of, and that's what makes it complicated, right? So in order to deal with this complexity, I'm going to talk about 2 different approaches right now, processes and threads, okay? To understand how these work, it's necessary for you to have a pretty good understanding of what exactly is meant by a process, what's meant by a thread. And I have a feeling that many of you haven't sort of looked at this in some years now. So I'm going to go through some pretty basic description of how a computer works. And if you've seen it before, that's fine. You're supposed to have seen this before. But hopefully what I'll do is to make it clear exactly how a thread works and how a process works, and maybe that will help you debug whatever difficulties you're running into, okay? So let's start, right at the beginning and see what a stored program computer is. So this is what's called the von Neumann computer. And this is due to John von Neumann, who's a pioneer in this field. If you ever want to feel completely like an insignificant worm, just look up von Neumann's biography. We are actually living in von Neumann's world. He invented computers and game theory. He could outperform supercomputers just by thinking about it. He's a brilliant mathematician. Also, was a policy maker, and was at the Institute of Advanced Studies. He worked with Einstein and people like that. And by the way, he was one of the people who invented the atom bomb. So anytime you feel full of yourself, just read his biography. One of the things he did in his spare time, more or less, was to write a small paper called How to Build Stored Program Computers, and this is what he said you should do. You have basically got what you call an execution engine. And what the execution engine does is that it can take an instruction and then carry out what the instruction asks it to do, right? Nothing really complicated about this. In fact, even your calculator kind of does that. You have a calculator, you punch in 2 plus 3, and it takes an instruction, 2 plus 3, and the execution engine gives you the answer 5, right? So far, this was invented by Pascal, actually, back in the 1700s. So this is not new. The interesting thing about what von Neumann proposed was that you would put the data 2 and 3 in a memory. Again, so this 2 and this 3 are coming into this engine like this, okay? Again, this is also not new. If you've ever seen a jacquard loom or any of these automated machines that weave cloth, they take memory, which is in the form of punched holes on strips of plastic or wood, and they execute the instructions, so to speak, what's in from memory, and they can do this. What Van Neumann proposed in addition to this is that what the execution engine itself is doing was kept in a program memory. So this we call data memory, and we have program memory, which has the value plus, and that goes in as well. So let me redraw this to make sure clear what's happening. So the instruction plus is coming from here, and the data is coming from here. And so what happens is that the execution engine is being told what to do and on what to do it with, both from memory, and both of these memories are sort of the same memory, okay, like so. So it's just one memory, and part of it is the data memory. It says this is what you're going to operate on. And the other thing the execution engine can do is to take the results of the execution and stick it back into the memory like so, the data memory like so. Okay? So now the first instruction therefore says add these two numbers, put the result over here. The second could say take 5 and add that to 3 and so on, and that's what. And this idea, which dates back to about 1942, 1943, something like that, is exactly what all computers do today. Right? Nothing has changed essentially since then, other than refining it in many, many different ways. But this is basically what's going on. So you have an execution engine, which is called the CPU, the central processing unit, and we have memory, which is called the RAM. And in this RAM, or random access memory, what we do is we store some data, and we store program instructions, and the instructions go into the CPU, and so we have what's called the fetch, decode, execute cycle. So you fetch an instruction, you figure out what it is, so the CPU does in this case, it's doing the fetch, decode, execute, and then go back to it, and just keep doing it over and over again. So it fetches instruction, decodes it, says, okay, I'm supposed to take this value, add it, put it here, okay, did that, what do I do next? And you keep doing this, and that's how a computer works, right? So everybody familiar with this, I hope. This is something you should have seen about 3 or 4 years ago. Okay. Let's now focus on the memory over here. So the memory is like so. And we usually organize it. We organize it like this. Okay, so maybe I need to talk a little bit before I go into memory. Let me talk about procedure calls. Okay, so I'm going to leave this up. Let me talk about procedure calls, what happens in procedure call. Okay, what happens in a procedure call is that we have organized our memory into some chunks like this. So this can be thought of as I'm just going to call this instruction 1, instruction set 1, there's instruction set 2. Okay? And what we're going to do is that somewhere inside over here, we're going to jump into the instruction set 2, execute all of it till the end, and then go back to where we came from. All right? So that's basically it. So I want to basically say over here, go execute subroutine something, instruction sets over here, it enters here, does its stuff, and goes back. Okay, that's a procedure call. When doing a procedure call, what we want to do is to have this set of instructions have access to some parameters that are being passed to it. And the parameters are being passed. So when it says it goes over here, it also says, oh, and by the way, here's some parameters. What we do is that we typically have over here in something called a stack. Okay, so is everybody familiar with the stack for procedure passing, pushing and popping onto stack? Okay. Anybody not familiar with it? Stack? Yeah, okay. So what we want to do is that we want instruction set 1 wants to tell 2, for example, here are 3 parameters, okay? But it can't give it the parameters in any way other than what it does is it puts the parameters over here, writes them over here, and then when instructions set these instructions want the parameters, it knows to look over here. Okay, we have something called the stack pointer, and the stack pointer tells you where the parameters are. And then if it calls another set over here, it moves the stack pointer up, and this instruction sets 3, because this could in turn call something else. Sorry, at the beginning it's going to do something and come back. So you need to kind of grow the stack up over here, right? So the parameters, the instructions 2 according to instructions 3 are placed on the stack over here. Okay? All right. Now, I've already shown you actually what's going on. You see that the instructions are actually growing in this direction, and the stack is growing in that direction. And this is how we typically organize memory, just to keep stuff very clear. We have RAM over here, and what's called the data segment, or the data part, goes, in this case, I'm showing it from the top growing down, and the stack is from the bottom going up. Okay, and some computers organize the other way around. Okay, stack grows from the top down and the data goes from the bottom up. It doesn't really matter, it's just a convention. In this case, I'm showing you the instructions. So whenever you want to call a procedure call, what happens is that the compiler is going to create the instructions and lay them out in memory from the top going down. And then when the stack is growing, it grows up. Okay? All right. The part that's important is to realize that this space over here is private to instruction 2, the set of instructions to the procedure call called instr2. This shaded area belongs to this over here. Okay? We put some things on it as parameters, but the rest of it belongs to this one over here, and any memory variables that are local to that procedure belong over here. All right? And nobody else can see them, okay? In the sense that nobody else should care about them because they're just local. And when this terminates, that part of the memory goes away. Okay? That part of the memory goes away. And at this point, when this terminates and goes back over here, we pop the stack, and then you're left with the private instructions for private data for INCR1. Okay, so what we see is that as we execute the procedure calls and return from them, the stack grows and diminishes. But at each point in time, we know exactly where the stack pointer is, and we know exactly what the private, anything from the stack pointer until top of stack is private to the currently executing procedure. Okay, it's private to that procedure. Nobody else can see it. Okay, any questions about this so far? Okay, and this is basically something you should have seen a while back. Okay. If you understand this, then you can understand processes and threads pretty straight. It's very, very simple to understand once you got this model straight in your head. That's why I want to make sure that you have this straight in your head. Okay, can I move on? Yeah? Okay, so let's look at how to deal with what a process is. A process, sort of by definition, is the instruction counter which is also called the program counter. Okay, it's the register set, and then it's the memory state. This includes the stack pointer, which is also a register. So a process is basically where am I in the program? Okay, what's in the registers, which is sort of an extra memory, plus what's in the memory. Okay, that's the process. If you want to tell you what the process is, it's these things. There's a few other small things which I'm not going to talk about, the exception stack and interrupt state and stuff like that, and co-processor state, which are things you don't really need to know about. But as far as you're concerned, this is what a process looks like. Okay, it's basic. So if I were to take all this information and write it somewhere, okay, and I read back, and I would be exactly in the same state. So that's what happens when you put your computer into a hibernate state. So you have a laptop, and you close it. What happens when you close it? What happens is that the instruction counter value, register set value in the memory state is all written onto flash or hard drive. Okay, and when you open it up, what happens is you basically reload everything back over here, and you started off, it's exactly where you left off. The mouse is where it is, the program is doing what it's doing, everything is exactly the same place. It's like somebody put you into hibernation. They freeze-dried you and put you in a casket, and then 10,000 years later, somebody rewires you and you're back up and running. Okay, unfortunately, you don't know what happened in the last 10,000 years, and you can't fly like everybody else, but at least this is the way this works. So for computers, it works pretty well. Okay, so what we have with the process is a special system called fork. It's like the fork in the road. Okay, so you go like this, and you fork in two different ways. And one of these, so this is one of these is called the parent, just by convention, and the other one is called the child. Okay, so so that's what's going on. So what is the fork? So basically, we have a process with these kinds of things, and one instruction away is a special instruction. It says fork. When this happens, essentially, all of the RAM, all the registers, all the memory state, everything is copied, and you get two copies. How do we do that? We take all of this stuff over here, make a copy down here, make all of this copy down here, and we give it a new process ID, each process ID. We give it a new process ID, but it is executing exactly the same instructions, the same procedures, everything is just the same. Okay? That's what a fork system call is doing. Okay? So what happens after the fork is that we have two instruction counters, two register sets, and two memory states, because everything has just been cloned, okay, exactly at that point. Okay? We have a problem, which is we need to know, well, as a programmer, we need to know basically, well, the code I'm writing, is it executing in the context of the parent or the child? So what we have is that we return a value. So we say, let's say x equals fork. So if x, oops. So if you say if, I don't know why I'm putting the parent as x, is equal to 0, okay? Then if this value returns 0, then it's, let me see, is it the parent or the child? It's a child, I think. It's a child, thank you. It's a child. Okay, when you're in this child, you can do whatever you want as the child, okay? But you have inherited everything from this parent, including the socket. So the parent opened a socket to some client. Whatever the state of the socket is, if it's in a listen or it's an accept or it's accepted already, you have a socket description table, all the stuff. There's a socket table, for example, is in RAM as well, so that gets accessible to the child. So basically over here, you can do child stuff, okay? Else, you basically do parent stuff. This is not good code, because what I really should be checking is if x equals -1, okay, then we are in trouble, right? We need to basically say if x equals -1, life is bad, something happened, abort the program. But I'm skipping that. I'm just showing over here with child open. Okay, let's just focus for a moment on what this child stuff and what this parent stuff means, and then I'll take a break. Let's go back to what you're trying to do over here. We have a bunch of clients, and they want to contact a server. Okay, it's a single server. So obviously, you're going to have something which is listening on some socket. It's got to happen, right? It's going to be listening on some socket. Well, it makes sense that the way to organize the program is to have something like this. You have the parent, and the parent is going to be basically listening, okay? And when it gets out of listen, okay, you know that it's got something ready to it accepts, right? Because it's something has contacted it. Now what we want to do is we want all the state about the actual interaction with the client to be with the child. You don't want the parent to worry about that. The child should take care of everything, right? So what you want to do over here is basically do a fork, right? And then if x 0, if it's a child, basically at this point you're going to do the game. Else, what you do is you just go right back here. Why do you go right back there? Because you're going to just go back. Now, this is not exactly what you have to do, because in this piece of code, each connection is its own child, but really we want a child to take care of 2 connections at a time. Okay, so you have to change this slightly. You kind of have to do listen, accept, listen, accept. You got 2, give it to a child. Let the child take care of the game. Okay, but it's a slight modification to that code. But basically, this is what it looks like. Okay, and what you see is that you got, when you say accept, you have S equals accept. So in this game, we can do read and write S. And that S that is being read and written to, which is a socket descriptor, you got from here, but that's okay, because remember, that S was something in the program, in the memory, and in the memory state, when you do a fork, the process memory state gets copied. And so this S that was referred to over here is perfectly valid over here, okay, in the child, right? And the child inherits the parent's state, okay, over here. Now, it's a you know, just to make sure you understand, you should realize that each new child inherits a little bit more about the parent's state, okay, right? But this is what's going on over here. Okay, I have to tell you one more thing about. Are there any questions about this? And I'll tell you one more thing. Any questions? Does this make sense? So how many people are using processes and forks to use it? Okay, so about roughly half. You did originally. You switched to threads. Okay. So the extra thing over here is that once the split happens, the child and the parent don't share anything. They don't share memory, okay? And so what you need to do is to explicitly set up shared memory between the parent and the child. So the way we do that is basically we have shared memory, and you have to say, what this means is that some part of the memory over here, like this, is going to be available to both, and the only thing we need to share in this program is just one thing, which is number of players, okay? But in general, you can make it as big as you want. And how to set up shared memory, it's pretty straightforward. There are a couple of system calls you can make that basically say, okay, I want shared memory, and you know, I'm going to share it with my children. Once you set up the shared memory child, you know, once you set it up, it's actually pretty straightforward. I'm not going to go into details of how that's done, but you do have to set up shared memory between the parent and the child. So the parent creates the shared memory, and then the child is going to then attach to it and use it later on, okay? And then they can read and write to it, okay? In this case, because we're not doing anything on the number of players, okay, it's not a critical variable, we don't actually need to lock it, okay? That's one thing I should mention. The locking is not required for the number of players variable, because who cares? It doesn't really matter how many people. If you get it off by 1 or 2, it's not going to cause any problems. You're not actually doing anything critical with it. So we don't need to lock the shared memory. In generally, you might need to do it. Okay, any questions about this? Okay, so after the break, I'll talk about threads. How many of you are using threads for your, so I guess the rest of the people using threads. Okay, threads. So, the difference between a process and a thread is important, and it can be summarized in just one thing that you need to remember. In a process, each process has its own instructions and its own memory and own registers. Everything is split, right? You can have entire process is split. Threads can be thought of as having just the ability to have multiple stack pointers. Okay, that's really what it comes down to. Okay, and that's it. Multiple stack pointers, and I should say, multiple program counters and stack pointers. And that's a thread. So let me redraw this to make that clear, what's going on. I'm going to draw the same exact RAM, but I'm going to show you the effect of that. So here's your RAM. And what I'm going to do is I'll draw the different, let me just use the standard term now. So I've got this in the procedure 1, procedure 2, procedure 3. So it's a bunch of procedures over here. Okay, that's fine. But what I'm going to do is at the bottom, okay, I'm going to allow you to have multiple stack pointers. So I'm going to have one stack pointer pointing over here, and it's growing, it's stacked like this, another stack pointer. Let's just start with 2. So I'll call this SP1, this stack pointer 2. Okay, and that's doing stuff like that. And just to, actually, let me just do it like that. And okay, so we have enough here to explain exactly how threads are going to work. Let's assume that we have PC, the first program counter is pointing to this one over here, proc2. Okay, so this means that we are sort of executing the instructions over here in the data memory, and that the stack pointer tells us basically over here. So I've drawn these two areas over here. These are the parameters that were given in, and this is private data. Okay. So this pointer plus some offset, some set of offsets are the parameters being passed into procedure 2. Okay. That's the way we press procedures. In addition, what we're also allowing is for this procedure to have private data, which is over here in this part, which is off the stack. Okay, so because it's in the stack, nobody else can see it, and we call this basically thread private data. Okay, it's private data, nobody else can see it, and the way we do it is that anything that's declared in the scope of the thread, okay, is going to be thread private data, just like you have private information. So if you have a function, you know, I don't know, let's say function dummy, and I have int x. Okay, this is a function in C, and I have int x over here. This x is private to this dummy procedure. This x exists as a memory location right over here. That's where x is sitting. Okay. And if we initiate a thread and say that the thread should be running procedure dummy as part of the thread, what will happen is that this is going to be in the thread private variable like that over there. Okay? We also have, in addition to this, some global space, which I'm going to shade like this. And if I define int y, which is outside this, then y is going to be sitting over here. So x is over here, y is over here, and this global is available to all the threads. They can all see it. Okay, it's in the global space. Okay. All right, and similarly, thread 2 could be executing process 3, so that would be PC 2, and then the stack pointer 2 is over here. So anything that's in the thread 2 is going to be, the parameters to thread 2 are over here, and all the thread private information is actually over there in the private information indexed off of stack pointer 2. So from the perspective of the process, what we have is that we can either run the program counter 1, or you can put it aside, take program counter 2 and its stack and run that. And you can put that aside, and we can do that. It's like a process. Just like we have two processes which have their own program counter and stack pointer and memory, here we have the ability to have multiple program counters and stack pointers. The difference is that in the case of multiple processes, we actually copying all the memory, okay, copying everything, and it takes time. Okay, it can take 2-3 milliseconds to do that. With threads, you're not copying the memory. Okay, all the stuff on the stack is private. It's kind of created on the fly. And the global stuff actually is the stuff that didn't get copied. It didn't get copied, so this stuff over here is not copied, so it's cheaper, so it's about 5 times faster. So if you create a process, versus, if you fork a process versus what's called spawning a thread, creating a new thread, it's about 5 times faster to spawn a thread. Okay. So to summarize, what happens is that to create a thread, we typically use a package such as pthreads, which is POSIX threads. And then pthreads has the ability to basically create a pthread. So you say create a thread, and you give it something like dummy. It's a few more parameters. And now when you say dummy, this means this is the pointer. This is the pointer to the function dummy. So this creates dummy as a thread. Now dummy is off executing. So what happens is that the program counter is set to the value of dummy. It's set to the beginning of dummy over here. It starts executing, and it has its own stack pointer. X is defined as int, so that's going to be put on private memory over here. And when 2 threads want to communicate with each other, all they need to do is change global variable like y over here. So if dummy were to say y equals 1, then that global variable y is set to 1, and anybody outside or any other thread that wants to read the value of y can read it. How do we use this? Okay, what we're going to do is that if we to implement the tic-tac-toe server using threads, what happens is that the main process, we don't have parent and child anymore, the main process is sitting there and listening. And okay, so let me just write that over here. So we have basically the same listen and then accept. Okay, s equals accept. Now you have one connection. Let's just do another one. So S1, S2 is accept. So we got 2 connections. Great. What we want to do is we want these 2 sockets corresponding to 2 clients to play a game, right? All the game dynamics that you wrote in the second assignment is now going to be put into a thread, right? And what it's doing is that we basically say pthread create, or whatever the exact thing is. Okay, something like game, and then you say S1, S2 are the parameters. It's not actually S1, S2. You have to define the parameters in a different way. It's not slightly different, but essentially what you're doing is you're passing in those 2 parameters, S1 and S2. And now the game over here is going to take those 2 sockets and do things as before. What we also have is that the number of players, if you call that num players, okay, we're adding 2 to it over here, and then when this game is going to exit, when the game terminates, it can actually decrement the number of players. This variable over here is actually available to all the threads. Okay, because this pthread create spawns off this thread, we can go right back to the listen over here, because that's a separate thread of control, which is actually playing the game, and it can terminate its thread, no problem. Okay, the parent doesn't die. It's sitting there on the listen accept loop over here. Okay, and that's the structure of the thread-based game, and that's basically all there is to it. It's not particularly hard. All you need to know is how to create a thread and how to update global variable, which is just changing the value of the global variable. That's all there is to it. Any questions about this? Yeah.
So wait, number of players
yeah.
is just total number of players in the server, or is it just in that particular one game?
It's total number of players in the server.
In the server?
Yeah. So initially you have 0. Say that again.
It can go above 2.
Yeah. Sure. Because let's say there are 6 players who join. So the first one comes in. So I could increment it by 1 each time. Just to be actually, if I want to be really precise, let me just call it number of players as being NP. So I'll accept. I'll do NP plus plus. I'll accept again NP plus plus. Okay, that's what's going to happen. And then inside the game, when I'm done with the when it's done, then I'm going to NP minus NP equals NP minus 2. I'm going to subtract 2 because I'm going to have 2 players end at that time, and that's the number of players. Of course, I have to be. This is there's a bit more complexity because if somebody sends me a question, is this how many players are there? I need to answer that as well, which I'm not doing over here. That would be in this game. Somebody asks me how many players are there. If they send me a question, then I'm just going to read the variable NP and send it back.
Oh, okay.
Yeah, because it's a global, right? NP is down here. So everybody can see NP. So threads, we don't have to worry about shared memory. Can I get it for free? Yeah. Yes?
So in the last part, everything closed down once there was a win, loss, and draw.
Yeah.
It seems like in this one, the server is still...
The server is going to be running forever. That's right. Yeah. Because it's a server, it's always looking for connections, always looking for work. So until you kill it, it's going to be on forever. So an internet service like this is, you can think of it as being eternal. As far as we are concerned, it's going to live forever. We want it to. Yeah. The number of games come and go, but the server is there. Yeah. Yeah. Any other questions? Okay. So I hope this clarifies how threads and processes work. You have to just remember this notion of program counter and stack pointer, which hopefully you remember, and the fact that threads have both private and global. And in the case of processes, when you fork them, everything is private. There's no global, so you need to create global separately. And you had a question? Oh, sorry, where? This one over here? I was saying when you're done, you say NP equals NP minus 2. Yeah. It just means I'm decreasing the number of players by 2 because 2 players finish the game. So when you're done. Yeah. Any other questions? Okay, so I'm going to erase this and then talk about one more thing and then we'll take a break. Procedure call. Okay. All right. So when I started doing work in, as a grad student it was 1988. Actually, how many of you were born before 1988? Okay, some of you. Gosh. Okay, so there were no thread packages, it turned out. I was trying to write threaded code, but there was no thread packages. So I found this guy in Columbia University who'd written a kind of a thread package, but it was too complicated. So I said, fine, I'll write my own. So actually, I wrote all the assembly code for my own thread package. And I learned exactly how thread works. When you're writing assembly code, you pretty much need to know how it works. And that was a great education. Anyway, I wouldn't recommend it. But in the end, I never used pthreads because I had my own package. Okay, and mine was much faster than pthreads. So I've never actually used pthreads in my life. Okay, let's talk about RPC, remote procedure call. Okay, so let's go back to this client server, and I'm going to change this a little bit and say that, let's say that the server actually makes a call to another helper server. I just call it helper. And what could that be? Let's say that we have a database of some sort, and one could think of the following situation. We want the clients to have a login and password before they're allowed to play tic-tac-toe. Okay, kind of a difficult, unusual thing, but certainly you need login and password to access your accounts on any online social network. You're talking about LinkedIn or Facebook or whatever. So you go to LinkedIn.com or Facebook.com, and you have a server over there that's accepting the network connection, right? That's pretty normal. But there's no reason why the database, your login and password, should be kept on that server. In fact, one would argue that you don't want to do that. What you really want to have is to have hundreds and hundreds of these front-end servers, right? Hundreds of servers, which are all responding to these things. And how do we pick which server to go? Well, DNS does that for you. So when you say resolve facebook.com, you come back with 100 different servers, and you pick one at random, okay? That's what Google does. If you remember from your first homework assignment, when you say google.com, you get back a long list of IP addresses. You pick one, and it goes to one of these guys over here. But they all need to use the same credentials for your Google Plus. Right? They all use the same credentials. So we want to have a single helper server with the database, and they all want to talk to the database. Okay? What is the database doing? The database is given a query which says, here's somebody's login, here's something password. Is it okay or not? Just very simple question. And that can be done for many, many people very fast by having a separate machine, right? And that's exactly what we do. We put in the database server. Now, in reality, it's not one database server, because if this goes down, everything goes down. So we don't want to do that. We actually have many database servers, but for now, we'll just pretend it's a single database server, okay? All right, so how do we do this? We would like to have the following bit of code, which says something like this: validate login password. So if validate login password is true, then OK, else try again. Okay, you want to kind of say, OK, go try again. Okay, this is sort of the bit of code. Where is this code running? It's running over here, right? This piece of code is running over here. Does that make sense? Okay, this is how you would do it. Question is, where is validate running? Okay, well, validate is not running here because what information it needs to do the validation is on a database over there. So what if we had this magic which allowed us to write code like this, just like a procedure call, but that validator is actually being run over here? Okay, so in other words, the procedure call was executing remotely. Okay, and this is what we call a remote procedure call. Okay. So in the remote procedure call system, what happens is that this helper server is going to export the ability. It says, if you send me a message on, on so-and-so IP address or in some location, which I'm going to export to you the function called validate. Okay? And what you need to do is to just send me the message, validate, give me two parameters, login, password, and I'll send you back a OK or not OK. All right? And from the programmer's perspective, they can just write code as if it was local. Even better, they can write the code locally, test it locally, and then they can just move it out over here, put it in this server, and then it will continue to work. Okay? That's the kind of the holy grail of programming for remote procedure call. Okay? But we don't need to worry about sockets. Don't have to worry about communication. Don't have to worry about validation of the code. All that is being done under the covers for you automatically. Okay? That's the idea of remote procedure call. Okay? The way this works is like this. Okay? When we call validate, this is what the memory looks like. So we have some stack pointer, and over here some parameters. And the validate is some program text that's sitting over there. That's the data instructions. So this is what happens when we have local call to validate, right? So we have some code over here, and we have some parameters over here. When you do RPC, what happens is that on the other computer, we have a process. I'll come to it in a minute. And we have validate sitting over here. And we have the stack pointer with the parameters over here. And we have something over here. Okay? So I'll tell you what's going on in those two boxes in just a moment. We set it up so that you declare this to be a remote procedure call. Okay? You declare validate is going to be a remote procedure call. And on this side, the system is saying, I am going to give you a remote procedure called validate. I'm going to give you a service called validate if you want. Okay? So what you need to give me are the parameters. And you need to tell me that I want to call validate. So on the socket, what happens is send a message saying, hey, I want to use your validate method, and here are the parameters. This piece of code sitting over here basically loads the memory with the code for validate, and it copies the parameters down over here, and then it calls validate. Okay, when validate ends, the results are sent back over here to this box over here, and this basically gives the results back over here to the place that called validate in the first place. So from this piece of code, it looks as if it was locally executed, except it was done under the covers. Okay. So let's see again what's going on in a bit more detail. So normally what would happen is that you would jump, the program counter would jump to validate, and the stack pointer would be set over here, and there'd be some parameters. Okay. Actually, what happens is that when you do remote procedure call, you do jump to validate. Okay. You do jump to validate in the stack pointer, except that over here, this is just becomes what's called a validate shim. Okay, it's just a dummy call. Okay, what this shim is going to do is that it's going to read its parameters and call this library function over here. Okay, it's saying here is my program text. Okay, so this is some parameters, and I want to call validate. And this piece over here takes the parameters and does something called serialization. Takes all the parameters, which could be like a pointer to a tree. It could be a linked list. It could be an array. It could be just integers. Whatever is on the stack pointer over here, it converts those into a long series of flat integers. Okay, everything is converted into integers and sent over here. What this does is it unpacks everything and puts it into parameters over here. Calls validate text, which runs as if it was, that's local, so it's no problem, and gets the results, sends it back over here. This, again, converts the results, which could be an update on a tree, for example, and puts it back into memory, and then goes back over here and says, here are the results. Okay? So from the programmer's perspective, it's easy. But from the system's perspective, it's quite hard, because what could go wrong, right? Well, this computer may die halfway through. So then what do? You call validate, but it didn't terminate. When you call a procedure, it terminates, right? Comes back, but here it doesn't terminate. It may take a very long time, because many people are calling validate at the same time, and so you may wait a second, 2 seconds, 5 minutes. When do you know it's actually been done? You don't. Okay, it may be either down, or it may be that it's busy, but you can't tell the difference. So this may actually end in a very funny way. If these parameters are complex, let's say that you have on the global state over here, the global, you have an array of size, an array of size 10,000, okay, or 100,000 for the sake of argument. And you're referring to one element of that array, okay, but you're passing as a parameter the pointer to the array. If it's a local procedure, it doesn't matter. You're passing a pointer to the array. You just access array element, 2560, modify it, and you come back. It's fine. With remote procedure call, the entire array has got to be sent over to the other side, okay? Because they don't, it doesn't know which one you're accessing. It doesn't parse the program code. It's just saying, well, is it pointed to a structure? I'd better send the whole thing, because I don't know what it is, right? And so if you aren't careful, you actually end up doing a lot of extra work. So while conceptually it's simple, okay, it is in practice quite hard to do. Okay, and so we don't use it all the time. For some things, if it's things like validate, it's really a good idea. Okay, because all you need to do is to send 2 simple parameters, login and password, 2 strings, and you get back a single integer yes or no. Okay or not okay, that's all. But if you do anything more complicated, it's not going to work. And so today, the most commonly used RPC is called XML RPC. And it's an RPC based on top of XML, which is the XML markup language. And it's quite commonly used. The other kind of RPC that's often used is in AJAX. So people have heard AJAX, right? So the AJAX, the X stands for XML. So this X is using XML RPC. So the J is JavaScript, okay? So what's happening is that the JavaScript is going to make RPCs all the time to the back end saying, give me something. So the most, kind of the first and probably the most widely used still AJAX implementation was for Google Maps, right? So what you have in Google Maps is that you know what it is. You have little you move the map, okay? So before Google Maps came out, you had these little boxes. You click, go north, go south. It was really quite painful. With Google Maps, you have a very intuitive interface. It's just like sliding a map. What happens is when you move the map, okay, you figure out what part of the map you need, okay? When you figure out what part of the map you need, the JavaScript is making an XML RPC to a function call that says, give me this coordinate. So give me, this is the current map, and this is what you need. So these are 4 coordinates, right? So you say, okay, I want the map corresponding to these 4 coordinates. Give me the rendering of it at this resolution, right? Because particular resolution rendering, and that's what's sent over here. So on the JavaScript, you send this message over to Google's backend server. They execute on their database and come back to you and say, here it is. The JavaScript says, hey, great, I got what I needed. I'm going to render it, and that's it. That's all there is to it. So the RPC works beautifully because all you're sending over is just 4 parameters, and what you're getting back is a simple JPEG. Okay, it's not much to do, and so this works very nicely for Google Maps. But it would be a mistake to use it for other things, and so this is, I guess, one of the best use cases for RPC. It makes the programming really simple. Any questions about this over here? So you geography guys, now you know how Google Maps works. All right. I'm going to stop with RPC. I'm going to move on to these 2 things, other things, transactions and PubSub. And I'm going to keep that over here. Okay. So transactions. I alluded to transactions earlier when we were talking about the bank issue. We had to worry about the checking account and savings account and so on. And transactions is kind of still the best way to do things when you have banks and things like that, things that have to be stable. But I want to be a bit more clear about exactly what a transaction is. So a transaction, okay, you can define it as a set of operations that satisfy the asset properties. Which are atomicity, let's see, what is atomicity, isolate, okay, what is C now? Consistency, isolation, and durability. Okay, those are the 4 properties. So if this is like a heavyweight approach to building reliable distributed systems, okay, you kind of, if it happens, it all happens or none of them happen, everything is guaranteed to be consistent, it's not going to be affected by anybody else, and once it happens, it stays happened, okay? So for example, you want to sign up for an account with, let's say, LinkedIn, right? So there are a number of steps that happen. You have to kind of go in and give your name and your email and da-da-da. At the back end, you have a database. When you want to update the database, you want this to happen. You want all these 4 things to happen. So once you've signed in, you stay signed in. Or once you have a membership, you have membership for the rest of your life, okay, etc. So the way we do it is that we essentially have support for these transactions in the actual system, in the distributed system. And I won't go into too many details other than saying that we typically don't use this other than for things where it really makes a big difference. You really care about it. For example, it would not make too much sense to use transactions for your Google Map update, right? We don't want to say, well, if I'm going to get these 4 different things. Stephanie, I'm talking about something here important here. Okay. So when you talk about Google Maps, you don't want to be saying, give me the 4 JPEG elements and do it in a transaction, because you don't really care. You don't have this necessity for atomicity. Okay? If you get it, it's okay. If it's out of order, it doesn't really matter, right? Whereas if it's a bank account, it's some kind of login credentials and so on, you do care about these things. So these end up being pretty heavy duty, and we don't actually use this very much in typical distributed systems other than big systems, banking systems, right? So when you go to Scotiabank's website and you say transfer money from checking to savings, we use transactions, okay? And there's a lot of work done on transactions which are being done when you have, so let me actually explain the transaction problem a little bit just to give you an idea why it's complicated. So let's say I have a checking server, and then I have a savings server which is responsible for the savings account, and then I have a front-end server which is doing the web, and then I have a credentials database which is giving me whether I have the right credentials or not. So I need to somehow, the front end, when you say from your web front end that say do a transfer, I need to make sure that the front end reflects the right thing, and the checking and the savings and the credentials database is validating it, and perhaps all of it has to be done at the same time, right? So we want to make sure that the state here and the state here and the state here, at least these three are always consistent. So what you do is you open a transaction, and then you do all these things, and then you close the transaction. Programmatically, not a problem. Implementation-wise, it's a problem because I initiate the transaction, I decrement from the checking server, and then I find the savings server is dead. So everything has got to be rolled back and have to coordinate the actions between these different servers, okay? And so implementing these transactions becomes really, really complicated and expensive, and that's why companies like Oracle have very large market caps, okay? They're very big companies, they have lots of money, and their servers are very expensive because they do implement these things. If you buy an Oracle distributed database, which has checking server and savings server front end, and you say, okay, begin transaction and do this, guess what? It's going to work, okay? And it takes a lot of doing. Okay? That's pretty much all I'll say about that. Any questions about this? Okay, the last thing I want to talk about is briefly about this thing called pub/sub or publish, subscribe. And this is just a very nice way of thinking about some kinds of distributed systems. And what surprises me is that the same idea is reinvented over and over and over again. Every 5 years, somebody thinks they've invented this new thing. It turns out to be publish, subscribe. Publish, subscribe is nothing more than what you would call Twitter feed. Okay. Okay, that's probably, or if you want to call it RSS, which is the previous generation of this. So what it is that you essentially have some kind of tag, and you add and assign, you have a bunch of things coming out with the tag, and then you can choose to subscribe to one or more tags, and so the whatever you choose to subscribe to will give stuff to you, okay? So one way of thinking about it is that we can think of tag one having a set of things coming out of it, and maybe I'll draw it slightly differently. The way I like to think about it is there's actually many companies that give you systems like this. We call this the information bus. And this is the tag one bus or feed one, maybe I should call it. And then you have feed two, okay, and then feed three. Okay, so each person is basically generating these feeds like this, and you can think of it as being sent down this wire. These are the publishers. And then each subscriber basically picks the one that they want, and they aggregate it up. So this is subscriber one. Subscriber one is getting feed two and feed three. Subscriber two is getting, so this circle means making a connection. This guy is getting, subscriber two is getting 1 and 2, and so on. So we can think of these publishers as being rows of a matrix, and the subscribers being columns of a matrix. And you just pick off the columns that you want, and you just pick them up. And that's it, basically. Okay, that's basically Twitter, that's RSS. In RSS, each feed is just a website. In Twitter, it's your Twitter thing. And this same kind of paradigm shows up over and over again. And it's, again, a nice way of building distributed systems. Okay.